Any questions at all? Okay, so then I will go ahead and review functions. So and like I said last time, that we see functions all over us in various areas. You must have seen the area of a circle, the area of a circle of radius r is given by a, which is pi r squared. And then I also pointed out a couple of other functions from physics. Position of a moving object as a function of time. The distance of a moving object as a function of time. Velocity of a moving object as a function of time. Speed of a moving object as a function of time. And also the spring restoring force as a function of stretch. So this is given by Hooke's law. The restoring force is negative k times x, where k is a constant here, and x is the amount of stretch. So if you have a spring, it has a natural position, it has an equilibrium position, and then you stretch it and let it go, and the spring goes back and forth, right? And so the stretch means the amount of displacement from the equilibrium position. Okay, so x is the displacement from the equilibrium position. Okay, so then F is the restoring force is given by negative kx, where k is a constant. It's called the Hooke's constant, I think. And we also saw some examples from economics, like commodity demand versus price. So here what I mean is the quantity of a specific product that is demanded by consumers at a given price. So given a price, what quantity of a product is demanded by consumers in a market. Okay, that's what I mean by commodity demand. And also commodity supply. What it means is that what quantity of a product is a manufacturer willing to produce and supply at a given price. What quantity of a product are the manufacturers willing to supply to the market at a given price? Okay, if the price is too low, you would expect that the manufacturers wouldn't want to supply that many products. If the price is high, they want to make more money, and supply more. Right? So that's the supply function. And then from finance, one example that we talked about was the asset price. As a function of time. So you can think of the stock, a Microsoft stock. So what is the stock price at a given time? Okay, so that's what I mean by asset price as a function of time. Now, I can go on and on and on and on and on with so many functions around a lot of areas. Nowadays, you name any area of study, you can find functions. You can. So, we have all these quantities that we study, but even more so, we study relationships among these quantities, right? We don't study time by itself. It's not that much interesting. But, if I look at time versus velocity, time versus asset price, it's more interesting. So you don't really just study quantities, you really study relationships among these quantities, okay? So all these examples that I gave, you see that you have two quantities, right? And two related quantities. Now, in all this, I think of one of the quantities. So all these quantities you can call variables. Okay. In each of these examples I gave you, in each example you have two variables, right? Two quantities, and they are related. One of them you should think of as an independent variable, and the other one you can think of as a dependent variable because. For example, time velocity. If you change time, you change velocity, right? So there is a dependency of velocity on time, right? So I can think of time as independent variable, velocity as the dependent variable in that way. So, and another key feature here you want to think of is that I think of all these relationships as input-output relationship or an input-output process. What's the input for velocity versus time? What's the input? Time is the input. Velocity is the output. So at a given time, what's the velocity? Okay. So all these relationships we have, I think of them as input-output process. Okay. You change the input, you may be changing the output. Okay. The output depends on what input you have. Again, for the supply price function, given a price, what's the supply, right? So again, input-output process. So what's the common app? So all these functions all over in different areas, economics, finance, physics, chemistry, all these relationships that we study, they have some common abstract features. So in mathematics, you don't care about velocity and time, right? So what do you care about in mathematics? Well, you want to study all these relationships at once in math, okay, together. And so what you need is the common abstract feature. The common abstract feature of all these relationships or input-output process, right? So again, so first of all, it's an input-output process. Given a value of the independent variable, you get a value of the output variable or the dependent variable. So A is a function of R. Given a radius value, you have an area value. At a given time, you have a value of the distance function. At a given value of x, you have a value of the restoring function. f of x, right? So first of all, the first common abstract feature of all these relationships is that you can think of this as input-output process. Input-output process. But there is one more important feature here, which is that at a given value of the independent variable, you don't have two different values for the dependent variable. Am I making sense? If you are given one value of the independent variable, it doesn't correspond to two different dependent variable values, right? For example, think of the velocity function. At a given time, a moving object cannot have two different velocities, right? Unless you are in a sci-fi movie or something. So at a given price, right, you don't have two different values of the velocity function. Same for speed. At a given time, an object cannot have two different speeds, right? At a given time, an object cannot cover more than one distance, right? So the feature here is that another example, at a given price, there will be exactly one value of one asset price, right? At a given time. So my point is, each input value leads to a unique output value. Okay, each value of the independent variable corresponds to a unique value of the dependent variable. Okay, so let me write that down. The second key feature is that each input leads to exactly one output. So in other words, what is valid for a function is that if I have a function, if I have an input value x, then it can only lead you to one output value y. Okay. However, so this is okay. This is okay for a function. To one input leads you to one output here. But if you have a relationship of two quantities where a input value gives you one input value leads you to two distinct output values, let's say y1 and y2, then this is not a function. This is not a function. It would mean that at a given time I have two different velocity values, right? So that's not valid for a function. But the other one is okay. Now, even though one input leads to a unique output, but one output can come from two different inputs. Am I making sense? So it is also valid that if I have two distinct input values, let's say x1 and x2, then both of them may lead you to the same output. Is that valid for a function? And the answer is yes. This is still okay for a function. From the examples that I gave, position, time, velocity, time, and so on, can you give me which example can have this situation? What's that? Yeah. So, for example, velocity, time, right? An object can have the same velocity at two different times. You can have, if you are driving your car, you can have the same speed at two distinct times during your travel, right? Am I making sense? So it is valid to that two inputs will give you the same output. So one way of saying that is that each input leads to a unique output, However, each output may correspond to two different inputs, right? Am I making sense? So what this means here is that an output value may correspond to more than one input. Okay, so we got, these are the main abstract features, common features for all the examples that I gave. And so in mathematics, for us a function is just this. A function is just an input-output process where it satisfies the condition that each input leads to a unique output. Okay. And just by, so now we abstract, we study all these functions abstractly. Okay, we just talk about functions in general, not specific. Our job is not study velocity time specifically. We want to study all functions at once. Okay. Okay, so once again, then, what is a? So I'm now going to try to give you a definition of function. First of all, again, remember that the way I describe the function is an input-output process. So let's say that I can think of this in the following way. So we are going to think of a function as a process. Okay, so f represents a function, and so here in this circular region, let's say I have all the valid input values for this function. So this contains all the input values. So let's say x is an input value, okay, and so if you give the function an input value x, what does it do? Well, it basically has a set of output values. So it leads you to a output value. Let's call that y. Okay. So first of all, the function is input-output process. Given an x, it spits out a output value y. We denote the output value for x. If we are representing the function by the symbol f, then the output value for x is represented by f of x. Okay? So, and the collection of all valid, so given a function, it has a valid set of input values. Okay? So the valid set of input values, that's called the domain of the function. Okay? It's a collection of all values of x for which the function makes sense. Okay? So the domain is, let me denote it by df. So df, if I have a function f, I'm going to denote the domain by df, and this will be called the domain. And what that means is it's the collection of all valid input okay, and all the output values they will make up the what we call the range of the function. Okay, so what's the range? So RF will denote the range. By the way, DF, RF, they are not standard notations in math. I am just using it in the class. So the range, this is the range of F, and what that means is this is the collection of all possible outputs. Everybody understands what I mean by input and what I mean by a domain and a range? Everybody's okay with that? Okay. Let's go over some examples to make sure we understand what a function is. So my first example would be on a function where the domain is finite. Okay. Now, if the domain is finite, right? If I am trying to express a function with finite domain, what's the easiest way of describing it? Well, because the domain is finite, I can just tell you the output value for every single input value, right? This is the input value, this is the output value. This is the input value, this is the output, because I have only finitely many. So that's what I'm going to do here. Let's say I have a function where the valid input values are only 0, 1, 2, 3, and 4, and the values of the function f of x is given by 0, 1, 0, 1, 0. Is that a valid function? Sure, because each input value leads to a unique output value, even though each output value may come from more than one input value, right? So that's okay. However, if I have this situation where x is again 0, 1, 2, 3, 4, and the values are 0, 1, 2, 0, 1, and let's say 4 is also associated with -1. So you have a process where 4 is associated with two different values, right? Then it's not going to be what? So this one is okay, it's a function, right? This one is a function, and this one is not a function, right? Not a function. Again, the difference is, in the second one, you have the input 4 leading to two different outputs, okay? Now, in this course, in calculus, we are not really interested in functions with finite domain, okay? So if you don't have a finite domain, then I cannot describe the function in a table like this, right? Either I have to describe the function in words somehow, describe the process in which the output is computed, or I have to give you some sort of formula to compute the output value given an input value, right? So for example, when we say f of x is 2x, for example, where now I say that x is between -infinity to infinity, then this is a function. So what is it doing, right? What's the input-output process? Well, what this is doing is that if you have input value x, right, how is it computing the output value? Well, the output is twice the input value, right? That's what the formula says. That if you have the input value x, the output value is twice the input value, right? That's what this function does, right? Is everybody okay with that? Okay, let's look at another example. Let's say I have the function g of x, and g of x is x minus 2, where x is larger or equal to 2. Okay. Oh, by the way, what's the domain in the first case? Well, I said this function is defined for x in that interval, right? So the domain is that interval. In the second case, I'm saying g of x is blah for x in this, right? It's for x greater than 2. So the domain is all real numbers greater than 2. Okay. So in the case of g of x again, what is the function doing? Well, if you have a input value x, the corresponding output value, how are you computing that? Well, you subtract 2 from the input and then you take the square root, right? So that's what this function doing. Subtract 2 from the input and then take the square root of the quantity. Am I making sense? So you're defining a function by using a formula here, and that's what we are. Those are the types of functions you're going to see in this course. Now, in calculus, oftentimes, probably 99.999% of the time, when you are given a function, they don't tell you what the domain is. Okay, they give you a formula for the function, but they don't specify what domain they are taking. Okay, so in that case, what domain would you take? Well, when the domain is not specified in the question, you take the domain to be the largest possible values of x for which the function makes sense. Is that clear? So this is a remark. If the domain is not specified, it is taken to be the largest possible set of inputs. So for example, let's say we are given this function f of x, and it is given by the formula x minus 1 over x minus 2. So what this function is doing, you give a input value x. What it does, it subtracts 2 from the input and takes the reciprocal, right? Now, the domain is not specified, so what do? Well, I take the domain to be the largest possible values of x for which this function makes sense, right? Well, what is that? Well, I see that I have a fraction, and in the denominator I have x minus 2. So this quantity will make sense as long as x is not what? 2. So we know that. So we realize that the denominator x minus 2 is 0 when x is exactly 2. So the values of x for which this quantity makes sense are the ones are all real numbers except for 2. Right? So what's the domain of f? It's all real numbers except for 2. And in interval notation, how do we write this? This way, right? Parenthesis around 2 means 2 is not included. Are we okay with that? Okay. And I'm going to come back to finding domains in a bit again. And let's go over some other examples. Let's say I have a function which is 2x squared minus 5x plus 1. The first thing that, let's say, we are asked to find is, hey, what is the value of f of 1? Well, how do I find the value of f of 1? Well, my formula is given in front of me, right? All I have to do is replace x by what? 1. And so I have 2 times 1 squared minus 5 times 1 plus 1, and that is equal to what? Negative 2. Okay, and how about f of negative 3? Well, this would be 2 times negative 3 squared minus 5 times negative 3 plus 1. And what is that? 18 plus 15 plus 1, right? So what is that? 34. F of 0. Well, that's pretty clear, right? It's going to be 1. And how about f of a? Well, again, you just replace x by a, right? So this would be 5a plus 1. And, okay, how about f of 3x? Well, let me show you f of x again. How do I find f of 3x? Sometimes people are confused when they see f of x is this, then what is f of 3x? What you have to do is just replace x by 3x. Okay? So when you have this function formula here, you know, what this formula says is that if you have an input value, you have to take twice the square of the input minus 5 times the input plus 1. So whatever the input is. So if the input is 3x, you take twice the square of the input again, minus 5 times the input plus 1. And so that is what? 6x squared minus 15x plus 1. Oh yes, I forgot to do that. Thank you. Let me use the eraser maybe. Okay, so that's 18x squared. And same way, if I have f of root x, then again, now the input is root x, so I take twice the square of the input minus 5 times the input plus 1. So this would be 2x minus 5 root x plus 1. Let me do one more like this. F of x plus 2. What would that be? Well, again, you should take twice the square of the input minus 5 times x plus 2 plus 1. Sometimes I see that students, when they try to find f of x plus 2, somehow instead of writing x plus 2 squared, they just write x squared. Okay, so be careful that you have to square the whole thing, x plus 2 squared. And okay, so this would be equal to what? Let me just say this is 2 times x squared plus 4x plus 4 I'm just multiplying x plus 2 and foiling it, right? Minus 5x minus 10 plus 1. And that's going to be basically 2x squared. 8x minus 5x is 3x. And 8, 9 minus 1. Okay. And a little bit more difficult example would be that, let's say, what was that number? 1 or? So I did 1, yes. Which one is 4x? Yeah. The second type of problem is finding the difference quotient. So you might be asked, find f of 2 plus h minus f of 2 divided by h. So a quantity like this is called a difference quotient. And so how do I find something like this? Well, we just do the following. What is f of 2 plus h again? Well, you take 2 times 2 plus h. So in the formula for f, you replace x by that, right? So 2 times 2 plus h squared minus 5 times 2 plus h plus 1. So this is basically f of 2 plus h, right? And then what is f of 2? F of 2, when you plug in 2, you get 2 times 2 squared minus 5 times 2 plus 1. And then the whole thing divided by h. So now all you have to do is simplify that. So 2 times 2 plus h will be basically what? Yeah, because we already found 2 plus x, f of 2 plus x, you just replace x by h. So this would be 2h squared plus 3h minus 1. And then from the second brackets, what do I get? 4 times 2, 8 minus 10, so negative 2 plus 1, which is negative 1, and then it's plus 1, right? Divided by h. So this would be equal to 2h squared plus 3h over h. And then I can factor out h. I get 2h plus 3 divided by h. And that's equal to what? 2h plus 3. So whenever you are asked to compute the difference quotient, right, f of 2 plus h minus f of 2 over h, maybe instead of 2 you might be given 3 or 1 or something else. Always your goal should be to get rid of h. Okay? Yeah.
On the question before this, where did you get this 2x squared plus 3x minus 1?
Let me go up.
On the very last part. Where did you get the minus 1 from?
Okay, so we had 2 times 4, and then minus 10 plus 1.
Okay.
So that's 2 times 4 is 8, minus 10 plus 1. That's
okay,
yeah. Okay. Any other questions? Okay. So let's go over, one of the very first question in your first exam is probably going to be find the domain of the given functions. And you might be given 2 functions and you have to find the domain of the functions. So let's do a little bit more practice on finding domains. So here you're trying to find domain. So let's say I have f of x. F of x is given by this x plus 2 and root of that. How do I'm not given the domain, so I have to figure out what's the largest possible values of x for which this formula makes sense, right? Well, we have a square root of a quantity, so inside the square root I am only allowed to have what? Non-negative numbers. So we need to, so the function f of x, so f of x is defined, f of x is defined, that means f of x only makes sense if x plus 2 is larger or equal to 0, right? Otherwise it doesn't make sense. And which implies what? Which implies that x is larger or equal to negative 2, right? So the domain would be everything to the right of negative 2, so that's how we can express that.
On the test, would we need to write that sentence?
Interval notation.
Just interval notation.
Yeah. Another example. Let's say I have the function g of x. It's given by 1 over x squared minus x plus minus 2. And again, the same question, what's the domain? So in this case, g of x is defined as long as the denominator doesn't vanish, right? So I have to figure out, I have to find out the values of x for which the denominator is 0. And then from the domain, I simply exclude those, right? So what are the values of x for which the denominator vanishes? Well, all I have to do is solve, right? I have to solve this equation, and that would mean I can factor out that quantity as what? X minus 2, x plus 1, which implies that x is 2 or x is negative 1. And so how do I express that in interval notation? So my domain is all real numbers except for negative 1 and 2. On the number line, which you don't have to include in your answer, I'm just showing it to make sure you get how to get the interval notation. Here is negative 1, here is 2, and you have to exclude negative 1 and 2 and include everything else. So the domain of G would be everything from negative infinity to negative 1, exclude negative 1, then from negative 1 to 2, exclude 2 and negative 1, and then from 2 to infinity again, exclude 2. So that's how you need to write the answer in interval notation. Is everybody okay with that? Another example. What if I have the function h of x, and that function is given by x squared minus 9, and in this case, once again, what do I need? Well, h of x is defined. H of x is defined if x squared minus 9 is larger or equal to 0, which means that x squared is larger or equal to 9. And if I take the square root on both sides, and I'm taking positive root of both sides, On the left hand side, I'm going to get absolute value of x. On the right hand side, I'm going to get 3. So if the absolute value of x is larger than 3, right? What does that mean? It means that, on the number line, let's say here is 0, and here is 3, and here is negative 3. Absolute value of x, it's the distance between 0 and x, right? Absolute value of x means the distance between 0 and x. Well, we are saying that distance is larger than 3, right? So that would mean that x gotta be where? Either here or here, right? So x could be only here or here, okay? And do we include 3 and negative 3? Yes. And so the domain is what then? The domain of H, everything from negative infinity to negative 3, union 3 to infinity. Okay. Is everybody doing okay with that? Okay, what do we mean by by the graph of a function? So graph of a function f of x. What do we mean by that? Well, for a given function, right? For any given function f, you can look at the collection of all ordered pairs like this. You pair up each input value with the corresponding output value. So remember, f of x represents the output value for the input x, right? So you pair up the input and the corresponding output, right? You look at all pairs like this. So you look at all pairs of the form x f of x, where x varies over the domain of f. Okay? So this is a collection of ordered pairs where the first coordinate is an input value, the second coordinate is the corresponding output value. So you have all these ordered pairs, and the graph of f means that collection of pairs. Of course, visually, it means that you plot these points on the plane and you get the visual representation of the graph. But by a graph, we simply mean this collection of ordered pairs. Visually, we mean you plot it and see you get a curve. Okay. So how do we plot these points? Well, visually, the graph means that you have the x-axis, the y-axis, and let's say the graph of the function looks like this. Okay. So how are you coming up with that graph? Well, for each given value of x, right? So if you have a given value of x, you are coming up with the corresponding value of the output value, right? So this height is y. So given x, you look at the corresponding output value y. You have the pair xy. So this is the pair x comma, or I should say f of x. So y, remember y is f of x. Y is f of x. So for each input value x, you have the corresponding output value f of x. You have that pair, you plot it. So imagine that you plot all such pairs, you get a curve. And that's the graph of the function. So again, what's the height of the graph at x? The height of the graph at x is f of x, right? Everybody's okay? Alright, so I'm going to give you some examples of graphs tomorrow.